Alrighty, so building on the previous lesson, we're still on 4.1, alright, just part 2. Today's lesson really focuses on the vertex form and applying it to application problems. Alright, so if we look at this first example here, the following graph shows the height of the football, after X seconds after it was kicked. So Y meters, X seconds. So the reason it's highlighting this is that these Y values that you calculate actually have meaning that whatever value of Y is at, that is the height, right? So let's say you had a Y of 5, well, that would represent the football is 5 meters high, okay? And let's say you calculated some X value and you got a value of like 3, well, that means the football has been flying for 3 seconds. All right, so just understanding that these numbers, these variables, y and x, actually have meaning in application problems. So we are going to fill in, all right, this equation right here. We're going to fill in this chart based on this equation. And this equation is this graph right over here. So this is the graph y equals minus 5, x minus 2 squared plus 20. All right, so that's what we're looking at over here. So let's fill in the chart. Our A value is minus 5. Our H is 2. Our K is 20. So based off these values, we can say, well, there's a reflection in the x-axis because the A is negative. That A value, the magnitude of that A, right, the actual number is 5. So that means we have a stretch. So vertically stretched by a factor of 5. Not negative 5, 5. It's translated 2 units to the right because it's negative 2. And it's translated 20 units up. And in this case, because the A is negative, we know we are going down, opening down. So the vertex, remember it's always at your H and your K. So the H value is 2, but the K value, and the K value is 20. So what does that 20 mean in the context of this problem? Right, because that is a value of 20 on the y. Well, that tells us the maximum height of the ball, because again, this is a y coordinate. This is a y value, and y values talk about the height of the ball. So we have a maximum height of our ball at 20 meters. And when did it occur? What time did it occur? At 2 seconds. Okay? That's what that 2, that h value represents. So, standard form, all right? We've talked a lot about standard form before. We can change an equation in vertex form, y equals minus 5, x minus 2 squared plus 20, to standard form by expanding. So what that would look like is if you have this equation, y equals minus 5, x minus 2 squared plus 20, and if you want to bring this into standard form, you need to expand it. So what that looks like is you taking that squared bracket and writing it twice. So you're expanding it out. And then we do the whole distribution. So minus 5, all right? But you take the x times the x here. So x squared, x, all right, foiling it out, remember? Minus 2x, minus 2 times that, minus 2x, and then the last one, negative 2 times negative 2, gives you plus 4. So then add that 20 on the back side here. Let's collect our like terms inside the brackets, so that's these right here. So inside the bracket, so outside the bracket, nothing changes. It's still minus 5 multiplied by your bracket, x squared, and then that simplifies to minus 4x plus 4 plus 20. And now we can distribute this negative 5 in. So that negative 5 goes through all terms. So that negative 5 times x squared is minus 5x squared. That negative 5 times this 4x here, plus 20x. And then this negative 5 times this 4 on the backside, positive 4, becomes minus 20. So those brackets went away, but then remember, you still have this plus 20 on the backside here. So plus 20. So then this negative 20 and this plus 20 go away, and you're just left with y equals minus 5x squared plus 20x. And again, that negative 20 and that positive 20, like they turn into 0, okay? I'm going to put that 0 just to make it very clear the next part, the next thing we're filling in. But notice how we went from vertex, and then we got to standard. Okay, you had to go this direction. You had to expand, right? Eventually, in the next lesson, we will go the other direction, and this is something called completing the square, okay? We've done this when we talked about factored form, like going back and forth between standard. So completing the square. There's a way to go the other direction as well. But this is coming up, okay? So not right now. So the constant term, the c value, so again, what does a c value mean? And well, c is coming from this standard form equation. So notice the a is the thing that's attached to the x squared. So this would right here would be your a value. The b is the thing that's attached to the x. So there's your b. And the reason I wrote the 0 is because you can see there's your c value. It's 0. So the constant term, the c value, is, well, the c value, as we learned previously, is the y-intercept, okay? This shows that the graph has a y-intercept of 0. And technically it's 0, 0, because you always have an x-coordinate of 0 on a y-intercept. But now in the context of this problem, because it's a y-intercept, it tells us the initial height, okay? So y values are measuring height. So the y-intercept tells us the initial height of the ball when it was kicked. Since a is negative, the graph opens down, okay? And again, why does it tell you the initial height? Like, there's two parts to this problem. Initial height. Well, again, look at what that y-intercept is. It had the coordinate 0, 0. So this means this is the height of 0 meters, and this 0 right here means at a time of 0 seconds. Right? We showed why this value is 0, right? That's what we calculated from right here. But again, it's a y-intercept, so this value right here, x is always 0 at a y-intercept. So that's why it is 0, 0, okay? And now again, just thinking about what those points actually mean in the context of this problem. So we've already talked a lot about factoring form, or factored form, sorry. So factoring changes a quadratic equation from standard form to factored form, all right? So remember, if you were given factored form, if you're given factored form in the previous unit, you can factor, oh sorry, no, the other way around. If you were given standard form, you factor to get to factored form, and then just like vertex form, you expand to get back to standard form, okay? Well, if an equation can be factored, that's the key word, can be factored, then the following information of parabola can be determined. Well, at the x-intercepts, remember, your y's are 0. Well, if it can be factored, that means your x-intercepts, and if this is our factored form equation from pre-unit 2, remember, those would be at the coordinates r, y 0, and s, y being 0. This information tells us the football hit the ground at, well, r or s, whatever those values are, seconds, okay? Because, again, why is it hitting the ground just like the previous problem? Well, the y values on a intercept, on an x-intercept, are 0. This means this has 0 height at, or i.e. ground, at r seconds. That's why it's r seconds. And then this one right here means same thing. 0 height, i.e. ground, at s seconds. Okay? So write the equation of the quadratic function in vertex form in standard form. So I'm giving you a graph and write the equations. Well, start with vertex form. Okay, so big picture here, we're going to create our vertex form because that one is, you can quickly look at your graph and determine it. And then from there, we will eventually expand it to get into standard, all right? So to create a vertex form equation, remember you need your A, you need your H, and you need your K. Okay, so you need those 3 variables. Well, you get this from just looking at the vertex. So the vertex is at the point right here, and that corresponds to -2 and 18. So the vertex is at -2 and 18. So that means you have y equals a, x, and because it's at -2, all right, that means you're going to have this whole thing being +2, square that, and then +18. Last thing we need to get is we need to find this a value right here. Well, to get that a value, just pick any point on the curve and solve. So a nice obvious point is right here, and that is at the coordinate 0, 10. Okay, but you could have chose any other one that looks obvious. So we have 10 equals a, 0 was that point. All right, so actually let me just write the point. We chose 0, 10, okay? So I'm just plugging in 10 for the y and 0 for the x. So +2 squared plus 18. So 10 equals a times 4 plus 18. Get rid of the 18. So that's 10 minus 18 equals a, or 4a technically, because a times 4 is 4a. So it's -8 equals 4a. Divide both sides by 4. And then a is same as -2. So we have our vertex form equation. So our vertex form is y equals -2 x plus 2 squared plus 18. So let me just copy this. So this is vertex form. Well, if we want to copy, if we want to expand it out, all right, to get into standard form, well, let's expand it out. So first thing is expand this bracket right here. So that is y equals -2 x plus 2 plus 18, okay? Y equals minus 2. Do your FOILing. So x times x, so we get x squared. X times this 2 plus 2x. 2 times this x plus 2x. And then 2 times that 2 on the backside there plus 4. And then plus 18 still. Collect your like terms inside the bracket, so it's those two x's there. So x squared, and this becomes 4x. When I say this, I mean these right here. Plus 4 plus 18. Next, distribute the negative 2 into all three terms in the bracket. So this becomes y equals minus 2x squared minus 8x minus 8, and you still have that plus 18. So now collect your like terms, these ones right here on the back, and in standard form you would get y 2x squared minus 8x plus 10. So here is vertex form, and here is standard. Minus 2x squared minus 8x plus 10. So determine the zeros of the function f of x equals x minus 5 squared minus 36. So in the previous lesson, right, we're now finding our zeros from vertex form. So if we have f of x equals x minus 5 squared minus 36, just like always, you're looking for zeros when the y is equal to 0, or in this case we're not talking about y's, but when the function equals 0, when f of x equals 0. So that means this right here, 0 equals x minus 5 squared minus 36. So we're isolating for x, we're solving for the x values. It says determine, so solve, okay? This means solve. So bring the 36 over, so that becomes 36 equals x minus 5 squared. We'll now take the square root of both sides, and remember that you will get a positive and a negative version of this. So you'll have one scenario where we are talking about the positive version of the square root of 36, so that would be positive 6 equals x minus 5. And why is it? Remember, we got rid of the squared right here. Right, so this square root and this square cancel, so it's x minus 5. And then you have the other scenario where it is minus 6 equals x minus 5. So solving for x, bring this minus 5 over. So that's 6 plus 5 equals x, or x equals 11. I write the x on the left-hand side. It's easier to read. And then same thing here, bring the negative 5 over. So that is the same thing as minus 6 plus 5 equals x, or x equals negative 1. There is your second solution, okay? So determine the zeros of the function. Well, the zeros are 11 and minus 1. But therefore, the zeros are, and then put them as ordered pairs. So the 11 is at the coordinate 11, 0, and the other one is at minus 1, 0. Okay? Putting them in the ordered pairs helps you understand what it is you actually just solve for. So another word problem, okay? I think this is the last one of the lesson. Yep. A ball is thrown into the water from a cliff that is 155 meters high. So let's highlight this because it's a given point. The height of the ball above the water after it is thrown is modeled by the function h of t equals minus 5 t minus 2 squared plus 180, where h of t is the height in meters and t is the time in seconds. Okay, so I know we're not graphing this at all here, but let's just get a picture of what's happening here. Okay, so you have a ball, you're standing on a cliff, okay? So we have some cliff. This is our cliff. All right, and here's you. You are throwing a ball, all right, and into the water. So you're going into the water down here, and you are chucking this ball. So the ball is going to go up, and then eventually it is going to go down here, okay, and hit the water. Well, we are going to have a parabola. There's going to be a bunch of things that about this right here, and this is measuring the height of the ball thrown as time goes on, okay? Squared plus, I'm going to run out of room. H of t equals minus 5, t minus 2 squared plus 180. So you are measuring, essentially, the height versus time. So time is on this axis, and height is on this axis. And this is measured in meters, and this is measured in seconds. So when does the ball, part A, when does the ball reach its maximum height? And what is the maximum height? Well, when, again, that means we're looking for a time value. And what is the maximum height? Well, that means I actually want to know what is h of t at the max, all right? Well, let's think about that. Like, the maximum height of the ball would be right here, right? This would be at some time value, and it would be our maximum value. Well, that point right there is the vertex. And if I look at my equation that I was given, well, my vertex is at the h and the k. So my vertex is at the point 2 and 180. And what does that mean? Well, this right here means at 2 seconds, the ball is at, the height is 180 meters. And because it is a opening down parabola, because the A is negative, this is a max. The height is a max of 180. So therefore, at 2 seconds, the max height is 180 meters. Okay? So just see the patterns here. When you're given a vertex form equation and it asks for maximum height, and when that happens, very simple. You just state the vertex pretty much. So then, when will the ball reach the water below the cliff? Okay, so I'm asking you for this point right here. And that point right there would correspond to a 0 height. Because you're at the water. You're measuring how far off the water you are. Well, 0 height, well, that means your h of t is 0. Your height is 0. So let's just look at what that is. So if we have this h of t equation, minus 5t minus 2 squared plus 180, and if we're looking for when, okay, so when, you already know you're looking for a time value of some sort, but when it hits the water below, well, h of t is 0, so 0 equals minus, and just write what you have, other so far. Well, what does this mean to you? What does it mean when your only unknown is this t value here and you're setting the one side to 0? Well, we're looking for the x-intercepts or the zeros or the solutions, okay? And like visually, that looks like an x-intercept, right? It's when you're hitting the 0 on the height. So solve. So just like we've done, get rid of this 180. So 180 equals, so it's positive one side, bring it over to the other side, minus 5 t minus 2 squared. All right, get rid of the minus 5. So minus 5, divide this by minus 5. Okay, so these cancel. So what is 180? Divide that by 5. So top of my head, that's 36. Yeah, 36. So 36 equals t, t minus 2 squared. And then you take the square root of both sides. So always remember that you will get a positive or a negative version of a square root. So you have to look at both sides of it. So let's look at what is the positive version of root 36. Well, that's just 6. And that would be equal to, remember, your square roots cancel. So that would be equal to t minus 2. And then you have the negative version of that root. So minus 6 is equal to t minus 2. So isolate for t. So bring the negative 2 over. So in this case, that's t is 6 plus 2. T equals 8 in context, seconds. Oh, sorry, t minus 2. And then bring the minus 2 over. So it's t equals, I'm just going to rewrite it like this, plus 2. So then t equals minus 4. Well, minus 4 seconds. But again, time can't be negative. So this one doesn't work. So this is your solution. And again, go back to the problem. What this means is that right up here, you hit the water at 8 seconds. That's what you just found. And on the other side of it, if you were to extend this into the negative space over here, into the negative time, which isn't a thing, you would hit the water also at minus 4 seconds. That's what you found, okay? But that obviously can't happen. So, last question. When will a ball reach a ledge that is 100 meters above the water? This is a type of question that throws a lot of people off, but it's the same process as when will a ball hit the water. I'm giving you a height. So in the previous problem, it was when h of t is 0, but when will it hit a ledge that is 100 meters above the water? Well, this just means that your height above the water, your h of t, is 100. So in the previous problem, we took our equation, h of t, and we set it equal to 0. But in this case, we're just taking this and we're setting this to 100. Because I'm asking you, when is it the 100? But the same process. I'm saying, well, solve for t. So you don't change any of your steps. You still get rid of this 180. Bring it over to the other side. So that's 100 now, minus 180 equals minus 5, t minus 2 squared. So that's negative 80 equals minus 5, t minus 2 squared. Divide both sides by 5. So minus 5, minus 5. So how many times does minus 5 go into negative 80? Well, 16 times. So these cancel. T minus 2 squared. Get rid of your square roots. Get rid of your squared. So this and this cancel. And remember, you're going to have two possible solutions of a root. So you'll be looking at the situation when you have the positive version of the root So that's positive 4, and that is equal to t minus 2. And then you have the other scenario where you have minus 4 equal to t minus 2. Okay, so bring the 2's over. So you'll get 4 plus 2 equals t, or t is 6 seconds. Do the same over here. Bring the 2 over. So that's minus 4 plus 2 equals t, or t equals minus 2 seconds. And again, that is a negative time, so that one doesn't work. So then you only have one solution, 6 seconds. So therefore, height of 100 meters at 6 seconds. And visually, what does that look like? Well, go up to your graph, and we're measuring 0, so 100 would probably be like here maybe, and that would correspond to right here. There's the ball coming down and hitting 100 meters, and that would happen at 6 seconds. That's what we just found, okay? All right, so that is today's lesson, and there is the work we'll do in class.